So guys, in this lecture we will study rational and irrational numbers from a very different point of view. We will take a look at the decimal expansion of real numbers, and we will see if we can use the expansion to distinguish between rationals and irrationals. So let's start with the decimal expansion of these three rational numbers. Let's see what is the decimal expansion of 10 by 3. So that's 10, that's 3, 3 3s are 9, that gives me 1. Now 1 is smaller than 3, so I'll put a 0 here and a decimal here. 3 3s are 9 again, 1, 0, again 3 3s are 9, 1, 0, 3 3s are 9. So this will continue in the same manner. That means this is a recurring decimal and this is an infinite process. So in this case our remainders are 1, 1, 1, 1, and this will keep repeating. Why? Because this is a recurring decimal and this is an infinite process, and our divisor in this case is 3. Carefully observe the remainder and the divisor in all the three cases. Now our next case is 7 by 8. So 7 and 8. Now 7 is smaller than 8, so I'll put a 0 and I'll get a decimal here. Now 8 8s are 64. 64, 6 here. 6 is smaller than 8, so I'll go with 0. 7 8s are 56. Remainder is 4, I'll put a 0. Now 8 5s are 40. Now remainder becomes 0, which means this process is complete. So this is not a recurring decimal, this is a terminating decimal, and this process is finite. This is not an infinite process. In this case our remainders are 6, 4 and 0. That's it. In this case we had infinite remainders. In this case we have a finite set of remainders. This was a recurring decimal. This is a terminating decimal. And divisor here is 3 and divisor here is 8. Now let's go to the next scenario. That is 1 by 7. Now 1 is less than 7, so I'll put a 0, decimal. 7 1s are 7. 3, 0. 7 4s are 28. 2, 0. 7 2s are 14. 6, 0. 7 8s are 56. 4, 0. 7 5s are 35. 5, 0. 7 7s are 49. Now I'll get 1 as a remainder. And if you see carefully, in the starting also we had 1 and now again we have 1. So which means this whole thing will repeat all over again. Now see, I'll put a 0. 7 1s are 7. 3, 0. 7 4s are 28. 2, 0. 7 2s are 14. So if you see carefully, the remainders are repeating and these terms are also repeating. These numbers are also repeating. Now this is also a recurring decimal, and in this case our remainders are 3, 2, 6, 4, 5 and 1. And if you see, these will keep repeating again. 3, 2, 6, 4, 5, 1. That's because this is also non-terminating and recurring, just like this. And if you have to write the decimal representation of this, that will be 0.142857, and this will again keep repeating 1428857, because this is also a recurring and non-terminating decimal. So what are our observations from this? The first one is the remainder either becomes 0 or it starts repeating. The remainder either becomes 0 after a certain stage or starts repeating. So for example, in this case the remainder becomes 0. But in these two cases the remainder doesn't become 0 but it starts repeating. For example, 1 1 1, it's repeating. And in this case it's 3 2 6 4 5 1. After 1 it starts repeating again. After this one it will repeat again. Now the second observation is the number of entries in the repeating string of remainders is less than the divisor. So here what is repeating? Only 1 is repeating. So what is the number of entries? We have 1 entry. 1 is less than 3, our divisor. In this case 3 2 6 4 5 1 is repeating. So what are the number of entries which are repeating? 6 entries are repeating, and that is less than the divisor. Our divisor is 7. So the number of remainders which are repeating is less than the divisor. The third one is, if the remainders repeat, then we get a repeating block of digits in the quotient. So if your remainders will repeat, something in the quotient would repeat. For example, in this case, our remainder is repeating, so you would see in the quotient 3 is repeating. In this case, our remainders are repeating, and you would see 1, 4, 2, 8, 5, 7 is repeating. So if we keep on doing the calculation, 1, 4, 2, 8, 5, 7 will keep on repeating again and again. So basically on division of P by Q, two main things happen. Either the remainder becomes 0, for example this case, or it never becomes 0 and we get a repeating string of remainders. Now let's take a look at both of these cases separately. So the first case is when the remainder becomes 0. In this case, the decimal expansion terminates. This is our decimal expansion. 7 by 8 is equal to 0.875. In this case, the decimal expansion terminates and ends after a finite number of steps. See, now this is not an infinite decimal, it has terminated. It won't go on forever, it has terminated. This is a finite number now, 0.875. Now we call the decimal expansion of such numbers terminating. And the case number 2 is when the remainder never becomes 0. For example, this case where the remainder didn't become 0, or this case where the remainder didn't become 0. In such cases, the remainders repeat after a certain stage, forcing the decimal expansion to go on forever. Now this will go on forever. This will never end. This will also go on forever. We have a repeating block of digits in the quotient. I already told you there's a repeating block of digits in the quotient. Here 3 is the repeating block. Here 1, 4, 2, 8, 5, 7 is the repeating block. Now this expansion is called non-terminating and recurring. So how will you write 10 by 3? 10 by 3 will be 3.3333 and infinite. Here because 3 is repeating, so I'll write this as 3.3 bar. So this bar means that 3 will repeat infinitely. In the same way, 1 by 7 will be written as 0.14287 bar, which means this will repeat again and again. Bar means that term, those numbers are repeating. So now our conclusion is that the decimal expansion of rational numbers, they have only two choices. Either they are terminating or they are non-terminating, recurring. Now suppose if you walk on the number line and you come across any number whose decimal expansion is terminating, or a number whose decimal expansion is non-terminating, recurring, can you conclude that that is a rational number? The answer is yes. So if you come across any number whose decimal expansion is terminating, or another number whose decimal expansion is non-terminating, recurring, that number will be a rational number. Let's take a few questions now. The first is, show that 3.142678 is a rational number. So how will you show this? We can write this as 3142678 divided by 1, 2, 3, 4, 5, 6. So we have represented this number in the form P by Q, where P and Q both are integers and Q is not 0. Q is not 0. So this is a rational number. The next question is, show that 0.333, which means 0.3 bar, can be expressed in the form P by Q. So we have to show that 0.3333, this is a non-terminating recurring decimal, which means 0.3 bar can be written in the form P by Q. So now see this carefully. So we'll assume that X is 0.3333 up till infinite. Now because only one digit is repeating, only one, so I'll multiply it by 10. 10x, if you multiply this by 10, it becomes 3.3333 up till infinite. Now you can write this term as 3 plus 0.3333 infinite, and this is our x, so you can write this as 3 plus x. Now 10x is 3 plus x, which means 9x will be 3, which means x will be 3 by 9, which means 1 by 3. So this number 0.333 is also 1 by 3. So this can be written in the form 1 by 3, which is in the form p by q, where p and q both are integers and q is not 0. Therefore, this is a rational number and this is same as 1 by 3. Again, I would really recommend you to try these things side by side, because just by listening you won't be able to properly understand it. Rewind the lecture and try it with me. That will make you understand this much better. The next question is, you have to show that 1.27272727, which means we have to show that 1.27 bar can be written in the form p by q, where p and q are integers and q is not 0. So again, I'll assume this 1.272727 as x. Now since 2 digits are repeating, I'll multiply this by 100. So my 100x will be 127.272727. Now this can be written as 126 plus 1.272727. Now this is our x, so this becomes 126 plus x. So basically 100x is equal to 126 plus x, which means 99x is equal to 126. So my x will be 126 by 99. So again, this number can be written as 126 by 99, and this is in the form p by q. P and q are integers and q is not 0. So once again, I'll repeat the same thing. Keep this in mind. The decimal expansion of a rational number is either terminating or non-terminating recurring. So if there's a number whose decimal expansion is terminating or non-terminating recurring, it is a rational number. The decimal expansion of an irrational number is non-terminating and non-recurring. So if there's a number whose decimal expansion is non-terminating and non-recurring, that is an irrational number. So rational will be terminating or non-terminating recurring. Irrational will be non-terminating and non-recurring. Just write it down. Keep this in your mind. Now the next question is to find an irrational number between these two. Now of course, using the process which we did before, you will find out that 1 by 7 is equal to this and 2 by 7 is equal to this. Now both of these are non-terminating and recurring. This is also non-terminating and recurring. Now we have to find an irrational number between these two, which means you have to find a non-terminating and a non-recurring decimal between these two. So this is 0.14, this is 0.28. Of course, there will be many infinite numbers between these two. So let's take anything like 0.16234101000. Now since this is non-terminating, non-recurring, it's an irrational number and it lies between these two. So that was all for this lecture. Like this video, comment with your doubts, and do share and subscribe to this channel. Thank you for watching.